you all for coming so much, and welcome to the National Museum of Industrial History. Can everybody hear me?
Yeah, we can.
Okay. I'm Karen Mossinger, the President and CEO, and we've been looking forward to bringing you this special program for quite some time now. I know myself, we've had this piece out in Foundry Park for a while, and looking forward to bringing it in and cleaning it up, and it's finally inside the museum. Me personally, growing up in New Jersey, just outside of the city, I was fortunate enough to experience the skyscrapers, bridges, tunnels, and other engineering marvels that were manufactured by various Bethlehem Steel facilities. Madison Square Garden, Rockefeller Center, the George Washington Bridge, and the Verrazano Bridge, among the most iconic and visible. But underground and underwater, there exist some of the most awe-inspiring of these engineering marvels, the tunnels. And Bethlehem had their hand in these projects as well. I remember as a young kid, my mom used to take us into the city and going through the Holland Tunnel on the bus, and she would always say, okay, look out for the sign when we cross New Jersey into New York. So I do that with my kids now, so that was always exciting. So it's an honor here to have our renowned engineer, Trevor Shellhammer, and he's going to give us some more insight into the complicated process of tunnel building. Trevor is a graduate of Lehigh University in Bethlehem, Pennsylvania, with the BS and MS degrees in metallurgy and MS in quality engineering. He joined Bethlehem Steel's Loop Management Program in 1973 and started in Bethlehem Plant Operations in the Brass Foundry and Iron Foundry. Trevor eventually became Foundry Division Manager of the plant's 5 foundry and pattern shop. He also later managed operations in the Blast Furnace Division and Structural Products Division. In 1997, Trevor moved to Bethlehem's Homer Research Labs as a Senior Research Engineer, then Research Supervisor in Primary Process Research, heading the iron making, coke making, refractories, and continuous casting groups. He went through the transition to International Steel Group, Mittal Steel, and finally ArcelorMittal, currently the largest steel company in the world. In 2005, he left ArcelorMittal for Colt Foundry in East Stroudsburg as the Director of Engineering and Quality Assurance. In 2008, Trevor formed TVR Technologies, LLC, doing business as Shellhammer Consulting, and worked with select ferrous and non-ferrous foundries and iron and steel plants in North America. Trevor is a resident of Lehighton, Pennsylvania, and is married with 2 daughters and 4 grandsons and a granddaughter. Please join me in welcoming Trevor Shellhammer.
Thank you, Kara. You stole part of my talk there, which was the beginning, which was how do you get involved in tunnels? When you grow up on a farm in Palmerton, Pennsylvania, your first exposure to tunnels is groundhogs. And the other one is, it was a treat to get loaded in the family station wagon to drive on the turnpike to go through the Lehigh Tunnel, right? That's when it was a single tube. So I won't talk about the second tube of the Lehigh Tunnel. So yeah, that's the first experience I had with tunnels as a child. Well, you might ask, well, why did you become a metallurgist? Well, I thought it was a good paying job and I wanted to do something meaningful, but really I wanted to invent the Iron Man suit. What was the genesis of this talk? I know nothing about tunnels. I worked in the iron foundry and was really not aware of the history of tunnel making, but I'm a member of the Lehigh Valley Foundrymen's Association, which is a lot of foundries in the area here, and because most people are getting older and leaving us, I kept getting records from the organization, and along with that were the old flyers of the past meetings. And going through them and scanning them and making them digital, and I came across this meeting from 1954, which was on Bethlehem's role in constructing the Lincoln Tunnel. and it was given by Amos Proctor, who was the assistant superintendent of the iron foundry, which was a job that I had at one point. And I know Amos Proctor. When I started here, he was working in the main office, probably with Fred Harvey here. And so I knew the fellow, and he's a Harvard graduate, so he talked about making the tunnels. And along with that, records that I gathered through my time at Bethlehem in the plant was a file on a metallurgical report on the tunnel segments for the Lincoln Tunnel. So that's really how I got involved in it. As a side note also, if you notice, there's a molder's display of tools in the back. These tools were donated by my neighbor's mother, and her husband was a molder in the iron foundry, and he started in there in 1951. His name was Willard Kreitz, but don't call him Willard, let's call him Wimpy. And when he retired, he took his tools home because it was his personal property. And when you retired, you got your tools, and he had them mounted in the garage. And after he passed about a year ago, his wife said, "Would you want his tools?" And I said, "What does he have? An old bucket of molder's tools?" She said, "Come over and look." And when I saw them mounted like that, I was very impressed with how he valued those tools and individually mounted every spoon and lifter and trowel on a board to show what he did at the iron foundry for almost 40 years. And starting in 51, he would have been there at the time these tunnel segments were produced. So I did get a little bit interested in the history of making the Lincoln Tunnel, the third tube. So what I'm going to talk about is a little bit of history and what I call 100 years of Bethlehem Steel almost. I had a separate talk I gave on this to ASM, I think. And then I'm going to talk about Bethlehem Plant Foundries. Many people thought we just made I-beams here and so forth. And a little bit about tunnel history, and then the Lincoln Tunnel third tube. I would say some little known history, but this is the National Museum of Industrial History, so it's not little known. I don't even know if I have to go over this because most people know this, but in 1857 through 1904, Bethlehem had changed its name 5 times, starting as the Saucona Iron Company, ending up as the Bethlehem Steel Corporation. And they provided steel for many of the United States' most famous landmarks, as Kara said, and there's a list there. This is, I'm wearing the same shirt. This is embarrassing.
Have you washed it?
Did you wash it? This was taken around 20 years ago, 2003, on a return trip from South Korea to POSCO, which at that point was the largest steel company in the world. And Bethlehem had a partnership in research with POSCO researchers. And so we did a lot of back and forth projects with the Koreans. And on the way back, I had never seen the Golden Gate, so we stopped and I had taken that picture. A little more recent history. Everybody knows they entered a new chapter in their life in October 15, 2001. Chapter was chapter 11. And that happened to be memorable to me because that was my 50th birthday. So they declared bankruptcy on my birthday, and after that, the company was bought by Wilbur Ross and formed into International Steel Group, which was ISG. That was a very good company to work for, I will say, because they didn't really know anything about making steel, and Wilbur said, "I don't know anything about what you do in research, but the auto companies say we have to have research, so you guys just do whatever you want, whatever you're doing." Is that right, Ken? So yes, it was a great place to work. Going back to the foundries, which again, a lot of people don't really recognize that there were 5 foundries in the plant. The foundry division was part of the manufacturing division, and the manufacturing division had forges, tool steel, the foundries, press forge, drop forge, made all different kinds of products from wrenches to 200-ton ingot molds. And In the foundry side of the business, we had Ingot Mold Foundry, which was the largest foundry by tonnage, which was on the other side of the Mincy Trail. And they made ingot molds and stools for all the corporate plants, as well as some trade customers up to 70 tons. It was a large profit center back in the day and made a lot of money, paid good bonuses, and had a lot of high hourly rate of pay. Coming further west was a steel foundry. They made all types of steel castings, and they didn't have a melt source, so they ended up getting their steel from the electric furnace melt shop, which was right next door. On East Lehigh, we had the roll foundry, which cast rolling mill rolls. They had their own large 20-ton induction furnaces for melting iron, and that eventually became part of Beth Forge, which then was Centec, which was when they installed a centrifugal caster for rolls, and that was bought by another company. The iron foundry, we made ingot mold stools, forging molds up to 220 tons. We had deep pits. The building is still there, right across the street. It's a stone building. We made iron slag pots, miscellaneous castings from anything small, a little cast iron bushing up to the big ingot molds. And the brass foundry was called the jewelry shop of the plant, and they made anything in brass and bronze needed by the plant, mainly the rolling mills, spare parts for the mills. We made bearings, bushings, nuts, and washers. And then on the copper side was about 50% of the business. We made all the copper for cooling castings for all the blast furnaces in the corporation. So the brass foundry had a pretty good role in the corporation and made a valuable product. Here's a little map of the plant. You can see where the iron foundry is. You can see where we are, and that little green building was the electrical repair shop right here. Next door to us is the pattern shop on the second floor of this building, and the carpenter shop on the first floor. Pattern shops where all the patterns were made for the foundries in the plant. Very large pattern shop. You might also see number 2 machine shop. Here's the electric furnace melt shop next to the steel foundry. Here's the oil yards, which is, I believe, a casino now, right? And the blast furnaces. So the iron foundry. I'm going to keep hitting this thing. It is one of the oldest buildings in the plant. I used to say it was built in 1863 until the historians in the audience started correcting me. I think it was 1871 if I'm correct. And we had 2 cupolas there. Those are 2 Whiting cupolas, 84-inch diameter cupolas, and I believe they can melt about 20 tons an hour. They're fueled with coke. What you see in the front here is a big pile of coke. Now back in the old days, they were hand fed. Everything was charged by hand, but in this case, there was a charging crane that actually would help to lift the coke and the scrap and the pig iron to be melted. This is an old picture of the iron foundry from 1919, I believe. This is in not the area where the tunnel segments were made for the tunnels. This is the upper run, or the big shop it was called, because it had deep pits for making the big ingot molds. At this time, I think you can see possibly the supervisor with the bowler here and the vest, and these are all molders making molds with a clay bonded green sand. Now there was a Society of Industrial Archaeology meeting here in Bethlehem a few years ago, and they talked about the different tours they gave of the area, and they called them an embarrassment because there's a plethora of things here, but they called it an embarrassment of bridges, an embarrassment of slate, an embarrassment of cement, an embarrassment of iron. And each separate tour group went to see that facet of the meeting. There was no embarrassment of tunnels. And I think these people made a big deal out of bridges. Nobody pays any attention to tunnels, as Kara alluded to that fact, because they're underground. But this was an embarrassment of disasters because in '49 there was a fire, and you can see the cupolas here, and we burnt the roof off of the foundry, the iron foundry. So that building over there, the roof was wooden with slate, and they were pouring a large mold in a pit, and it must have been damp from a 150-ton ladle of iron from the blast furnace, and it blew up. So basically the iron, the molten iron, blew straight up and lit the roof on fire, and the entire roof burned off. So the roof that's on it now was replaced back in '49. You can see the vintage fire truck here. In '55 was, which one was that? Diane, Hurricane Diane, right? And you can see how that flooded the plant, and the museum would be back in here, I believe. So there's water out on 2nd Street and even 3rd Street. So that kind of closed the foundry down. So you got to be making this 3rd tube of the Lincoln Tunnel in between this time frame and this time frame. Fortunately, I think it was finished by the time of the flood. I stuck this in because Bethlehem was famous for taking a lot of pictures of their product. And they would stage the product on railroad cars, whether it was forgings from the drop forge, or castings, or structural steel. They'd have signs made up, and they would have, obviously, their own photographic services, their own photographers come down and take pictures of this, and they use it in their marketing brochures and whatever. And on this one, I just happened to find was it did have an actual Lincoln tunnel segment. This does not look like the one out in the hallway. This is from the Lincoln. That one is not, okay? I'll talk a little bit about that one at the end. But they would put their negative numbers on their official photographs, and you can see the size of some of the things made at the iron foundry. And on each side here were probably things made in Central Tool or the Drop Forge or something like that. But I have a ton of pictures of products made, ingot molds, slag pots, whatever the company was trying to promote. They would have official photographs taken. We'll get into the tunnel part of the talk. A little tunnel history. I think the promo that was on the web was the first tunnel underwater was under the Thames River in London, and in 18-something. Again, I'm not a tunnel expert. But the first one in the US was under the Hudson River between New York and New Jersey, starting in 1871. That had a lot of problems. They were using steel plate and brick. The company went bankrupt. It was started up again. It went bankrupt again, and finally it was finished. It took 30 years, and it was too small for railroad cars, so they didn't use it. So I think the next one to be constructed actually used the tunnel segment that's out in the hallway. But in 1890, under the St. Clair River in Port Huron, Michigan, which is a crossing into Canada, I believe, was the first use of cast iron tunnel segments. Very ingenious. You make these segments and you bolt them together in a ring underground, piece by piece by piece, until you get across the river. The method was successful, and this was the same method used on all the New York City Hudson River tunnels. And these tunnels were all made by Bethlehem. The first two are the Pennsylvania Railroad tunnels under the Hudson, and that's where one of where the casting outside came from. So that piece has been essentially underwater or underground for almost over 100 years, and pieces like it. And that's tunnel still being used today by railroad. In the 20s was the Holland Tunnel. and that's a twin tube automobile tunnel. It's a 29.5-foot diameter. Let me say that the railroad tunnel is only 18 feet diameter. There's 9 of those segments plus a key to tie it together. The Holland and Lincoln, there's 14 of those segments in a ring and a key to tie it together. In 1930s, the Lincoln Tunnel was built, and that's a 31-foot diameter tube, twin tube. And also the Queens Midtown Tunnel, twin tube. In the 40s, the Brooklyn Battery Tunnel, twin tube. And in 54 was the third tube of the Lincoln. They recognized they needed more ways to get to the city. The Lincoln was too congested, so they decided to build a third tube. When this was completed, it was the only 3-tube tunnel in the world. So all the above were built using Bethlehem supplied rings. Now, I have to say some of these rings were steel and some of these rings were cast iron. Mainly the rings under the river in the silt were cast iron. Where they went through rock, they ordered steel tunnel segments, and those were made at the steel foundry. But the majority of the segments were cast iron.
Why was that? Cheaper
Cheaper,
than steel?
steel stronger was needed in the rock areas. This is an artist's concept of the Lincoln Tunnel. It goes under the Hudson from Weehawken, New Jersey to Midtown Manhattan. It's 1.5 miles long. It was named after Abraham Lincoln, obviously. The other tunnel under the Hudson is the Twin Holland Tunnel from Jersey City to Lower Manhattan. They're all under control of the Port Authority of New York. The third tube was planned in 1950 due to high traffic volume. And the first contract for material for the third tube was awarded in 1952 to Bethlehem Steel for $10 million. They were the low bidder. They provided the delivery of 46,275 tons of cast iron and steel rings for the tunnel. And as you'll see in the next slide, I think I got this one from the museum from Andrea, they needed 1.2 million bolts to bolt them together. And work was stopped on and off for a strike. The tunnel got flooded at one point, and then there was some quibbling between New Jersey and New York politically, and eventually the tunnel got finished. When it was opened in May of 1957, as I said, it was the world's first tunnel with 3 tubes. It came in under budget, with the tunnel part of it costing $44 million. The castings were 10, the rest was the construction. This is a drawing of a segment very similar to the one in the hallway. This is for a railroad tunnel. As you can see here, this one calls for, well, I can't see, but this calls for 9 segments and a key. And here's a depiction of the bolt. I think Bethlehem would have been better off selling bolts. Maybe they did, I don't know. That I don't know. And there they are. They were saying it could lift up a locomotive. I have this poster somewhere actually here, I believe. Okay, this is how they did the tunnel. I'm more into the foundry part of it, but I'll take a stab at how the tunnel was built. It was called a shield-driven tunnel, okay? So they dug a hole in Weehawken, New Jersey, 55 feet deep, okay? And they put a steel ring in there with an edge on it, 31 feet in diameter, and that's here. That's the cutting edge of this steel ring. So they have hydraulic jacks pushing this steel ring through the silt. Where does the silt go? It falls down. How do you get it out? Okay, those guys were called sand hogs. That was their name. We need sand hogs. So these guys down here, they got to dig that out and put it in a car. They had rail cars, little rail cars going in and out. Ton new segments coming in to be assembled, silt going out. There's a bulkhead here that makes this pressurized. So you're under the river, they had to have it under positive pressure so no water seeped in. So you have to go through an airlock. So these men have to go through an airlock to get in, and all the cars have to go through the same airlock to go in and out. So here they are pushing them by hand. And as this shield is driven forward and the silt is removed, they assemble these rings. One by one, 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 for 1.5 miles. And they're doing it not only from the New Jersey side, but from the New York side. Did they meet in the middle? How many people have been through the Lincoln or the Holland Tunnel? It's a lot. How many people have been through the Lehigh Tunnel on the Turnpike? I've been through them both, and it's gives you the willies going underwater, but you know it's safe. The stuff was made by Bethlehem Steel. It's safe. So that's how it was done underground. When it was done, they had a big gala event here where the Port Authority came in, the contractors all came in, the employees came in, the people from the 13th floor or wherever, you know, plant managers came in, and they all wanted to get their picture taken with this mock-up of the tunnel. And I'm not sure, but that's a 1954, and that's a plant patrol vehicle, I believe. So again, I'll say the 31-foot ring is made up of 14 segments and a key. I don't even know, but if you can see, there's a key at the top, and there's 14 segments going around. It's very hard to see the joint. They're all fully machined on 4 sides and assembled. There's also, they tried to show the ventilation system underneath, and the attendant standing there, and the utility piping in the side. In the middle of the tunnel in the floor, I believe there's a sump for drainage. So that's a pretty good depiction of what the tunnel looked like. And there's your ventilation. They had 2 ventilation buildings, one in New Jersey and one in New York for air exchange when the tunnel was complete. I'm not sure if that guy's a dummy or if that's a real person. I think it's a real person. And I'm trying to picture where that was taken, and at first I thought it was at the open hearth across the street from the iron foundry, but the more I look at it, I think it's still in existence right up here, next to number 2 machine shop. Okay, so how did we make these? We'll get into the foundry part a little bit. It was green sand. It wasn't green, it's sand-colored sand from New Jersey. Actually, reading about it, it was a gravel sand, naturally bonded with clay. Basically, you dig a hole in New Jersey and you get clay bonded sand. And even at Ingot Mold Foundry, when I was there, we were buying this same sand from a hole in New Jersey, 2 truckloads every day coming into Ingot Mold. And it's the same sand they used here back in the 1910, 20, 30, 40, it's the same sand, okay? It's amazing that you can dig a hole in New Jersey, get sand with sufficient clay that you can make a mold. So you run it through a muller and you add some more water and maybe some extra clay if need be, and then you feed it into the hopper over the molding machine. Actually, they're setting a flask on the pattern. That's a pattern for the inside of the segment. That is called the drag, which is the bottom of the mold. And then once the flask is on, they fill it with sand, and a crew goes there and they ram the sand in. There was a crew of 20 men, made 80 to 85 of these every day for a year. This is a picture of making the cope. The cope is the top half of the mold. The top half of the mold is basically just the rounded part of the segment or the outside diameter of the segment. And they call this pattern a turtle back. It looks like a turtle's back. All it is, it's the rounded section. They put a flask over that pattern, fill it with sand, and they ram it just like they did the drag. Cope and drag molding is done the same way today. These were specially purchased machines. They were called jolt squeeze rollover machines. So that table jolted up and down. That's a lot of weight. So pneumatically it jolted up and down and compacted the sand, and then it was rammed by hand. Now when they finished the mold, I can't believe they actually have a stand there for the cope, because I've seen people stand under a mold like that to do the finishing without a safety stand. And I won't say where, but I've seen it. And this is 1950s. We actually have this special place. The guy even has a special light so you can see what he's doing. These guys are setting, that is what's called a bootleg core. I don't have a big bootleg core, I have a little bitty bootleg core. So it's just a little core that makes a hole in the casting. So he's setting that bootleg in the rib. It's going to cast a hole in there so they can put a clevis or something to handle it with. And he's finishing the cope. So when this is done, they'll take the cope and set it down, clamp it up, pour in the iron. And that's exactly what they're doing here. Setting the cope. There's a whole row, there's another row. Then they have to have a way for the iron to get in, so they put a pouring cup on there so the guy pouring the iron can get the iron in the sprue. And that's what they're doing here. Those are the two cupolas I mentioned. There's two 84-inch diameter cupolas here, and there's a spout. We're filling it, looks to be about a 10-ton ladle on the transfer car. Transfer car, same transfer car, 1973 when I was there through 1995, same transfer car used to transfer back and forth. So they would transfer iron from the cupola area into the bay where they made the molds for pouring. Again, they made 80 to 85 of these in an 8-hour shift. Now they had to wait approximately 6 to 8 hours after pouring before they could shake them out. But this is the chemistry of the iron for all the metallurgists here. It's a gray iron, which is gray iron is a flake iron, so the carbon is in the shape of a flake, like cornflakes. So if you cut it and polished it and looked at it, you'd have carbon. That's pure carbon flakes. That's what makes gray iron so good for cast iron pans. It's got a real good thermal conductivity. You make eggs and cornbread, whatever. But depending on the structure, it will have the different strengths. So here's the spec from the Port Authority. They specified two chemicals. Sulfur and phosphorus. Anybody could hit that chemistry there. That's 0.12 max. Our blast furnace could make that. 0.60 max phosphorus. That's a piece of cake also. And then the pouring temperature was between 2400 and 2500 degrees Fahrenheit. Then actually we had an internal spec because this was too loose for us at Bethlehem. So our spec for carbon, manganese, phos, sulfur, and silicon was even more restrictive than the customer spec, just to make sure we hit the properties that they were looking for. But it's gonna be underground for 100 years. Well, I forgot something. There's no tensile test on this, so I don't know what grade cast iron it was. It could be 25,000 PSI, it could be 40,000, it could be 55,000, high strength cast iron. But they did specify a transverse load test, which means 1.25 inch diameter bar, 15 inches long, put it on 2 stands, break it in the middle. It had a break at over 3,300 pounds. There is no ASTM spec for that today. I looked it up. It's totally different size bar, totally different parameters on the test, the modern test. But they did build a lab right in the iron foundry to test this metal every cast, okay? And pretty much most of them passed. They had a few instances where the castings had to go for annealing or heat treat, but this was a pretty successful chemistry to hit here. So looking it up and looking at the current transverse load test, I would guess that it was just a plain 30,000 class 30 gray iron, which would be plenty good enough for the application, although Mike tells me that they did take some samples from some of these segments from an old tunnel, and I have no idea what those properties were, but it would be very interesting. Okay, here's a picture. The key is larger than you think, okay? It's about 1 foot wide, but it's 2 feet long, or longer. It's this one here, and that's a segment. You can't really see it too well, but there were 4 bootleg cores to make 4 holes in these ribs. And what they do is they stick it in the sand and they put a nail in it to hold it. So there's still nails sticking out here. So those have to be ground off. But that's a very clean casting. And I don't see a BSCO or an I-beam or anything. There's some lettering on here, but it doesn't look like the one out in the hallway. Here's a picture of taking them over into the cleaning building, which is not there anymore. And they carried them by forklift. They had to be between 170 and 300 degrees Fahrenheit when they shook them out 6 to 8 hours later. And they would coat them with tar. The tar was kept at the same temperature. So this tar was coated on the outside as a rust preventive thing. And then they went through a shot blast machine. Well, they said, why did they go do that? Because it seems like the shot blast machine would clean the tar off. Well, they designed and built a special shot blast machine just to do these pieces, and it would only shot blast the inside part. It wouldn't touch the outside tar part. Strange. And then the rest would be hand chipped or ground by chippers and grinders, and that's what these guys are doing here with a hand pneumatic chipping gun. But I'll tell you what, those look pretty nice. Now they get machined, like I said, all the 4 sides where they get bolted together all get machined. And so there was a special milling machine to do each side, and a special drilling machine that drilled 20 holes at once. So there's a bit, there's a bit, there's a bit. There's 6 holes in the long side, 4 holes in the short side. That's 20 holes total. And these are some inspectors, I think, from the Port Authority that are no safety glasses, no safety glasses. 1954. And from what I read, this was machined in number 6 machine shop, which was adjacent to the iron foundry, which isn't there anymore. Now then there was a bunch of templates and check gauges that they had to try them with. There was an inspector on site here the whole time to check these things with these gauges. And there's all kinds of templates and check gauges. They check the holes, these templates, width, length, everything. Very thoroughly inspected, because they're gonna go underground and they're gonna be assembled under there. You know, you want the bolts to fit, right? When they were done, they got sent to the east end of the plant, where we had a lot of storage area, and they stored them. It was a lot, okay? And they would send them into New York or New Jersey as needed. So it was like almost like a just-in-time type of thing. We stored them here, shipped them by rail in as needed. They'd unload them in New Jersey or New York, and they'd go right underground. So 'cause they didn't have a lot of room there to store stuff like that. Some more pictures of getting your picture taken with the big assembly. And then there was the test ring. They had to assemble a test ring after they were machined to be inspected, so that they were sure, even though they already inspected everything, once they got it to the job site, they would be able to bolt them all together. And you can see how this is all done. I forgot to mention, each one has a grout hole in it. So that one out there, you'll see there's a plug in it. There was a hole in there. When the ring got done, they would pump grout in there to seal the gap between the segment and the hole they drilled, the hole they bored. So the whole segment on the outside was sealed with grout. And that was part of the purpose for the tar coating, because it was going to be covered with grout on the outside. A lot of these pictures came from a metallurgical report. And if you ever worked at Bethlehem, you're very familiar with the metallurgical reports from the metallurgical department, which was up in the Navy building. And they would issue these reports, and I have a copy of their report on the tunnel segment project. It includes a lot of metallurgical information, a lot of photographs, and other information. Okay. The internet is great. I didn't have any of these pictures, but you can find them online. And it's interesting to see working underground with these big pieces, handling them with pulleys and rolls, basically, and bolting them together. And here's another of putting the railroad track in. There's an airlock. These things are going in through an airlock into the tunnel. And these are more. That's not in. That's not the right one. That must be it in there by mistake. And this was taken when they met in the middle. Well, that could be the right one. This was taken when they met in the middle at the New York, New Jersey boundary. Somehow they knew where that was. And that, okay, that's putting on the subway tile that everybody likes to put in their kitchen. And there's a picture of it, modern times. Now, if you think making tunnels was easy, because there were no fatalities on this project, zero. This was a tunnel, a recent tunnel in China that was being constructed under a dam or a lake, a reservoir, and it's made from cement, and it broke through, and there were multiple fatalities. And that was just in 2021. So now, you've probably read about a new tunnel project to New York and called the Gateway Project, which has been kicked around for a long, long time and got politically stopped and started and stopped and started. And Governor Christie didn't want it to happen, and they couldn't agree on how it was going to be funded. But now it's been funded, hopefully. And they're going to be putting in 2 new rail tunnels under the Hudson. Again, called the Gateway Project, because for $16 billion. As I mentioned before, segments were $10 million, $1954. The whole project was $40 million. This is $16 billion for for 2 tubes. And because of Superstorm Sandy, the existing 2 rail tunnels were flooded, and they found the chloride in the seawater was affecting the cement. Not that the cast iron itself was damaged, just the rest of the tunnel and the utilities and other piping. So there's a picture of some of the damage. So, celebrity in the audience. So what are they going to make the new tunnel out of? Cast iron? Cement. Apparently, I'm not sure, but Lehigh University is doing some testing on some of these pieces, and are they actually for tunnel?
I'm not sure. I can find out, Trevor.
Okay.
Yeah.
I'd be interested to go up and see them sometime and learn more about them. But that's a little bit bigger than a cast iron one that we have out here, and I don't know how sandhogs would be handling that underground, but apparently there's a new way to build a tunnel that involves those pieces. All right, now this one out here. It was in a kind of rusty condition, I guess you'd say, stored in Phillipsburg, removed from the tunnel for investigation work, and 2 of them were in storage. The story is from when one of them was stolen, and the thing's got to weigh 3,000 pounds. How do you steal something like that? But this one here is being on loan to the museum, so we tried to take a look at it and see where it came from. It actually came from Bethlehem Steel, from the Uptown Hudson Tunnel, which goes under the Hudson, and 1910. So it's over 100 years old, and I still can't lift it. And that's the picture was out on the segment out there. It's from one of these tubes, and it just amazes me that there's so much a network of roadways and railroads underground in New York that this schematic just is crazy. And I asked our local county map person if he could get me a map of all the tunnels in New York, and he said no. So there must be a lot of tunnels, and I still haven't found out how many. But underwater tunnels, there's not that many. That's another one. That one there's a write-up out there. You know, it flooded. Construction was stopped. There was a strike. Somebody was killed. A bunch of people were killed. But the 2 tubes were finally completed, and still in use today. And that's pretty much all I have. Anybody have any questions?
Yeah, during the period of time in the foundry, how many people were employed in the foundries? There had to be quite a few with all the work done with all those segments being made every day.
I found an old historical write-up. Apparently, in the 40s, somebody in the plant management said, let's write up the history of every department. And I heard somebody had the history of Central Tool written up in 43. I happened to come across the history of the iron foundry written in 43. I came across the history of the brass foundry written in 43. So somebody was on a history kick back in the 40s, and they said, let's put a history together. And it has a production of these departments. There were older cupolas over here at the beginning to make these segments, not the 2 big cupolas I showed you pictures of. There were littler ones off to the side. And a list shows there were 70 molders working there in 1919. When I was there, we only had 69 people in the whole shop. And this was 70 craft molders. So there were a lot of people. I don't know exactly how many. But we were producing 2,000 or 3,000, 4,000 tons a month, probably what they were producing with 5 or more times the number of people than we were producing the same tonnage with in the 70s, 80s, and 90s. But a lot of manpower was in the foundries back then. Everything was manual. You know, the cupolas were charged manually at the beginning. The sand was all shuffled manually. It was all wheelbarrows. And as the things got modernized, there were fewer and fewer people. But there were a lot of people. I don't know exactly how many. And in '54, when my neighbor's father was working there, I don't really know. I just know, when I started, it was under 100 people. I mean, I know at Ingham Boulder used to be 400 people, and then whittled it down to maybe 150. So as automation came in, and you got forklifts and, you know, different material handling equipment, you needed less manpower. So the number of employees went down, and basically your production stayed the same or went up. Yes.
Yeah, but like the iron foundry, we converted that to no-bake sand. And
Right.
there was a lot of work done in the iron foundry.
Yeah, they spent $11.5 million in 1977 to get rid of that sand that is from New Jersey, that you dig a hole in the ground, and get rid of that clay bonded sand, because you couldn't see from one end of the building to the other, am I right? With the old sand. It was dusty in there, and silica became a problem. And Mr. Kreitz, that's his tools, had silicosis. He was the last person in the foundry diagnosed with silicosis. And he wouldn't leave the foundry. You know, he could have been a janitor in this machine shop or whatever. No, he was a molder, he was staying there. So environmental found one area of the foundry, which was a small casting area. Through sampling, there was no silica exposure. So he said, I'll be a molder in that area. And that's where he went until he retired in 1989. And he was a molder, and he wanted to be a molder. But the no-bake went in, which was a chemically bonded sand. So you would mix the sand with a binder and a catalyst, and it would cure like concrete. You didn't have to ram it like you have your little metal pouring display here, and you have to tamp the sand into the little flask to make your little tin knick-knack part. With chemically bonded sand, you didn't have to do that. You just mixed it in a mixer, dumped it in the mold, and in 20 minutes it was hard like concrete. So that reduced a lot of manpower, and the reason it was put in for $11.4 million was environmental. Basically, they put in dust collection, they put in this new sand system, and all of a sudden you could see from one end of the building to the other. And the building was 360 feet long, so it was nice to see the other end of the building. Also, there was never concrete floors in that foundry. When we concreted the floors in that project, we had a supervisor retire. I said, John, why are you retiring? He said, I can't walk on concrete. He said, I've been walking on sand for 40 years. I can't walk on concrete. It hurts my feet. So he retired. But it was all an improvement. Concreted the floor, put in dust collection, and again, less manpower needed. Anybody else?
When they took that section out, they had another section to replace it?
Mike might know when they took that out?
Yeah, they took that out. They didn't take that out from the underwater part. They took it out from a part that was actually on the island of Manhattan. So I have to look up what they replaced it with. That's a good question.
Anybody else? Yep.
How many individual segments made up the third tube? Do you know that?
30,000.
30,000.
30,000.
Were they running 2 shifts to do that, or 1 shift?
They would pour, mold and pour on the day shift, and they would shake out on the middle shift. And it was that way when I started there, same thing.
The
Yes.
Holland Tunnel was first before Lincoln.
Right.
Were they made the same construction system
Yes,
for building the Holland?
yes. In the historical document I have, in 1919, I think it was, they got the first Holland Tunnel order, and that basically set them up for a year and a half. And they made enough money on there to buy more new equipment for the next tunnel. And so they became like a tunnel specialist. Among everything else they were making, tunnel segments were just one part of the business they were making. But yeah, everything was made the same way pretty much.
What was the difference between the key segment and the other segments?
The keys,
Yeah, what was different about the key segment?
just the size.
Just the size.
Yeah, they had to put 14 of these big pieces together, and they had this little gap to fill. And they had to pull everything together with the key.
Thank you.
So what was it pushed into that slot?
If it fit, yeah. Right, right. And if not, they had to winch it together or jack it apart to get that last little, better than struggling with a 6-foot piece. Okay, they used this little 1-foot piece.
What was the purpose of the air chambers?
Underground?
Yeah.
Don't know. I don't know. It was an enclosed airlock. So I don't know what the pressure
That was to
under
keep the
there.
water out.
It was under pressure to keep the water out. I don't know.
Similar
And the
to-
airflow in the tunnel now, I don't know. But that's what those big towers are for.
You said the
Ah,
test
I
piece,
told you, no questions.
you said the test piece was done right in the foundry. Well, that was an unmachined piece, so you're only
Right,
controlled over 1.25 inches for the square was what you molded for that test piece.
right, right,
So that was molded in the same sand you were pouring the
Right.
casting in.
right, right. It's very funny, a lot of aluminum specifications, even today, have unmachined tensile bars. Surprise me, but they are.
What's your opinion then of moving to concrete for the
No.
Gateway project?
Definitely don't like concrete or plastic. I got one word for you, iron.
Is that done because there's nobody to make it anymore, or is it?
I had a whole piece at the end of the report, the green report, talked about this possibly being the last tunnel constructed this way. And it had reasoning for that. They said, number one, it's safe. Because prior to the third tube, there was an underground Holland tunnel, chemical tanker exploded. Okay? And we were talking about driving under there and seeing water dripping and you think it's leaking. No, this tanker exploded in the Holland tunnel, in the middle, and nothing happened. Okay? It was safe, no damage. Well, maybe some tiles fell off, but the rings, everything's intact. So it was safe. The reason was, all these people were specialists, sand hogs. And it was usually the grandfather, the father, the son, they were all going into the same business. And by the 50s, nobody wanted to do that anymore. Your kid didn't want to do that. Now I'm gonna go into make apps for an iPhone or something like that, right? So in the 50s it was the same thing. Nobody wanted to be a sand hog and work underground anymore. So they were having trouble finding people, and they said it'll probably be some alternative to doing tunnels this way. And it turned out, I guess, trenching became the next way to do it. Because have you been through the big dig up at the Logan Airport in Boston? They didn't go underground to do that. They trenched it and sank the tube sections underwater. From my understanding, they were made at Sparrows Point shipyard down in Maryland by Bethlehem Steel. And they transported them up to Boston. They trenched a hole in the bottom of the river and sank these steel sections together and joined them. So, because nobody wants to be a sand hog, I think the thing went the way of the buggy whip.
Well, the environmentalists don't want people to be sand hogs because they were subject to the bends working in a compressed air environment. So there was a terrible environmental disease to working as a sand hog.
Probably, but I guess it probably paid pretty well.
Yes, you did get an environmental.
Again, no fatalities on the third tube. I think that's important.
Which tube was the third one from the Jersey side?
It says south,
Okay.
but I'm not sure that's correct. But the report I showed says it's the southern tube, whichever one that is.
Yeah.
Yeah.
What's the core when you pour the segments? Is the core wood? when you make the mold, there's a core, right, that you gotta take out?
There's no core. You have a cope, which is sand shaped like this, and you have a drag, which is sand shaped like this. And when you take the flask apart, the sand falls away, and you pull out a hot piece.
I think he means the pattern.
The pattern?
Yeah, there's something, when you make the mold, there's like
Okay.
a core in there, right, that you gotta take out to pour in.
If I understand you correctly, the patterns were made here on the second floor in the pattern shop, and they were made, the coat patterns were made out of cast iron, so they would wear, because you're making 1,000,000 pieces.
Right, so you
And-
reuse them.
And the drag patterns were made out of wood, but they were lined with steel, because you were using them over and over. And there were 2 sets of every pattern, because one was constantly being maintained in maintenance, because they were making 85 a day. And people handle them very roughly.
Do you know anything about how the channel between Germany or between Britain and France was done? Channel tunnel?
The channel?
The channel tunnel.
Nope. No, I don't know how that one was done. I would imagine
They have a tunnel boring
it
machine.
was bored.
Boring machine.
Okay, if you notice, tunnel trivia, the first tube of the northeast extension between exit Channeltown and Lehighton is square, rectangular. The second tube to the west is round. Why is that?
Tunnel boring machine.
Because they bored it through, because the Austrians know how to make tunnels, because there's a lot of tunnels over there. And they hired the Austrians to come over and drill that one, so it's round. You can't drill a square hole, can you? Okay, so yeah, that was bored. That's above ground though, but I imagine probably the tunnel was made by boring. They got these machines now that'll drill a hole underground and run electrical wire and everything. And they just find them. They got fracking drills. I mean, they can go do amazing things. All right?
So the cast iron pieces were made over here.
Correct.
And some were steel, they were cast up there.
At the steel foundry. I think I had a picture or 2 of the steel foundry ones, but you know, I tried to keep it about the iron foundry. And basically they were made the same way. The only difference is steel shrinks a lot more, so I mean, they had to do a little bit different with the patterns. There was a 1/4 inch of finish on them, which is not much. And if you look at that piece out here, you can see a little relief where they machined it. There's still a little bit of finish left. And a 1/10 of an inch shrink rule on a cast iron. Because if it's supposed to be a foot long, you have to make it 1 foot, 1/10 of an inch. Because when it solidifies, it's going to shrink 1/10 of an inch. In steel, it's 3/16 of an inch. Okay, thank you.
What's the life of cast iron versus concrete? Like it's 100 years old. Is it gonna go another 100 years? Is it inert if it doesn't get wet? You know, the rings.
There's historical castings in India. There's historical chain bridges in England. There's stuff that's hundreds of years old. I don't think that's a problem. Thank you very much.
Doing this report gives you tunnel vision.
Yes.
Pulls down the mold, you have to get it out, so you go down and get it out. These are like trowels where you smooth things. Those are called shafts. Yeah, nice to meet you. Gives us a lot of help.
Did you take that picture of that tunnel?
Yeah.
Is that, I wonder where they came from.
Yeah.